On the night of the 7th of September, while the moon slid into Earth's shadow and the world grew a shade quieter, something astonishing happened to 3I Atlas. It is the kind of quiet pivot that makes astronomers sit up and rub their eyes, the kind of turn that takes a story you think you know and bends it into a different shape. A month earlier, spectrographs insisted the visitor carried virtually no diatomic carbon, the very stuff that paints many comets with a ghostly green. And then, beneath the dimmed sky of the eclipse, Atlas bloomed. A vivid, unmistakable emerald aura blossomed around the nucleus, as if a hidden switch had been thrown and a new script handed to the cosmos. That glow wasn't a subtle trick of processing. It wasn't a camera quirk or a mirage born of thin air. Photographers like Jurger and Raymond captured the transformation plainly, the way you'd capture a lantern igniting in a darkened room. The coma, the soft vaporous envelope of gas and dust, shifted from a muted reddish cast to an emerald that shouted chemistry in motion. It was a declaration that whatever lay inside this interstellar body had crossed a threshold. Something that had not been present or not been visible now was. Only weeks earlier, observers at Kitt Peak had hunted carefully for carbon chain species and come up empty, or almost so. The absence was emphatic enough to suggest diatomic carbon couldn't be a major player. And yet here we were, a green float of light, the signature hue ordinarily associated with exactly those molecules. It invited a cascade of questions. Had the sun's heat finally burrowed deep enough to liberate reserves of carbon species buried beneath crusted layers? Were we seeing chemistry that doesn't typically run in the comets that formed near our own sun? Reactions that require the particular blend of ices and organics forged around another star? Or was the glow, provocative as it looked, not diatomic carbon at all, but a different molecule with an overlapping fingerprint, something rare or simply uncharted? That would be a revelation in itself, a hint of chemical pathways that thrive elsewhere but have left only faint footprints here. A hint that the goo and grit that built Atlas came from a kitchen with unfamiliar recipes. Even as the colour story exploded, another thread pulled taut. Brightness. By mid-September, the comet's light curve was running ahead of nearly every prediction, accelerating faster than models had dared. Data collected in the comet observation logs showed the object departing its expected script, discovered around magnitude 17 and then rising to the 12-14 range by the end of the month. Brighter than interstellar visitors had any right to be, though still in the realm of telescopic pursuit. Brightening that quickly means outgassing on a grand scale, and unlike the slow, steady ramp many of us envisioned, the power seemed to have been gathering itself earlier. That earlier activity had already left a trace. When Dr. Adina Feinstein and colleagues combed through images from NASA's Transiting Exoplanet Survey satellite, they found signs that Atlas was awake in March, beyond Jupiter's orbit, where most comets are locked in silence. It was as if the engine had idled far from the sun, then picked up speed the way a dream accelerates just before you wake. This is not how our local comets behave. It suggests either an unusual stock of ices, carbon dioxide and carbon monoxide perhaps, ready to sublimate at lower temperatures, or a structure that lets sunlight penetrate and stir things earlier than expected. And then came the observation that made even seasoned astronomers pause. Hubble's sharp gaze, turned towards the comet in July, caught a feature that doesn't sit comfortably in standard comet physics. An extension of scattered light appeared to stretch toward the sun rather than pointing away as a classic tail does. Corrected for geometry, the extension ran roughly 10 times the width of the coma itself, a slender, luminous finger pointing sunward where radiation pressure should be herding particles the other way. An anti-tail can form under certain alignments, yes, but this specific shape, with this prominence under these conditions was unusual enough to send teams back through the data. As you track along with Aetolus' passage toward perihelion, you might have felt buffeted by a flurry of headlines, some careful, some breathless. Part of the confusion, sadly, has been self-spreading. Viral claims about a second massive comet barreling inward have less to do with new discovery and more to do with conflation. The slow, far-off approach of Bernardinelli Bernstein, a genuine giant, is being mixed in with the current arc of 3I Atlas. One is immense but distant, on a path that won't bring it anywhere near the bright inner solar system for us. The other is here, changing, puzzling, and revealing. The algorithms are better at amplifying drama than at untangling timelines, and if you've seen headlines promising two Leviathans at once, it's likely that blend at work. The data that matters is quieter, and it's piling up day by day. Atlas's cyanide production, for instance, is rising according to a steep power law with an exponent near 9. That's not a curve that strolls upward, that's a curve that climbs. It hints at chemistry or structure we don't typically see, microphysical processes that become abruptly efficient with only slight changes in temperature and illumination. It suggests internal layers waking in a sequence, fractures opening new pathways, or reservoirs that remain sealed until some thermal key turns. Observations gathered by Tess, stitching together faint frames, show the comet stirring earlier than it should. Activity beyond Jupiter points to volatiles like CO and CO2 taking the lead over water ice. In our neighbourhood, water is often the main actor when comets brighten, switching on as they cruise through the frost line. Here, the script looks different, and with each additional night, more numbers stack to reinforce the impression. 3I Atlas is playing by rules we've only partly written down. Even the geometry of that sunward feature grew more dramatic under scrutiny. Avi's analysis of the HPE frames, pushing through the problem of viewing angle, suggested the phenomenon is stronger than initial naive looks would imply. That revision doesn't just tweak the detail, it presses on the fundamentals. If solar radiation and wind are expected to drive material away from the star, what mechanism aligns particles or light to build a plume-pointing home? Could dust dynamics, shaped by gravity and projection, mimic a sunward fan under this specific alignment? Could outgassing be collimated by topography on the nucleus, vents that act like nozzles, carving a jet into the space between the coma and the sun? The candidates are on the table, but none feels like a comfortable fit yet. The good news is that help is on the way in the form of fresh vantage points. In about 2 weeks, Atlas will pass within tens of millions of kilometers of Mars, and instruments built to scrutinize the red planet will try to wring secrets from a single pixel of comet light. Spectrometers aboard Europe's Mars Express and the ExoMars Trace Gas Orbiter will tilt outward and listen for lines that Earth's air tends to hide. High-resolution cameras, normally fixed on canyons and crater rims, will switch modes briefly to watch a moving point in the black, hoping to catch a textural hint in the coma or a feather of jet structure. Perhaps the numbers will nudge our models back toward ordinary physics with a cleverly chosen angle. Perhaps they'll push us deeper into the unusual. Before we go further, settle in, breathe. If drifting off to stories of strange ice and ancient light is your kind of quiet, consider tapping like and subscribing to Space Historian. It helps more than you'd think, and I'll keep shaping these deep dive lullabies to carry you towards sleep. Back to our Emerald Comet. Imagine Atlas as a long-cooled room, shutters closed for eons, now slowly warmed by the sun's attention. Doors that never swung open in the deep interstellar night begin to loosen. A hinge pops, a seam breathes, Gases that once rested in locked pockets finally find their way into the light. Some of those gases fluoresce. Others carry tiny solids with them, grains that scatter starlight in peculiar ways. The changing colour is not just aesthetic, it is a chemical verdict delivered in photons. For months, the colour read a sober red, what you'd expect if the outer layers were dust-rich, if complex organics and weathered grains dominated the mix. Then, quite suddenly, the green entered. If it is diatomic carbon, it means molecules we could not sniff out earlier are now being minted in the coma or freed from interior stores, or both. If it is something else, another species with green fluorescent lines, then we are on the edge of naming a behaviour we haven't properly catalogued. Either way, the threshold behaviour matches the brightness surge. Once some critical condition is met, temperature, porosity, stress, the comet doesn't just brighten, it blossoms into a different regime. Meanwhile, the brightness path itself is odd. Some specialists, comparing the rate of brightening with families of comets we know, find the curve resembles that of dynamically old objects, bodies that have looped through the inner solar system repeatedly and bear the signatures of many heating cycles. But that reading clashes with the fact that Atlas is interstellar, a one-time visitor. How does a stranger wear the mask of an old friend? We could be witnessing a coincidence of metrics, or we could be staring at a limitation in how we classify comets by light alone. The sunward extension, call it an antitail if you like, casts a longer shadow over our expectations. Classic comet tails point away from the sun because photons and charged particles shove dust and ionized gas outward. An antitail typically appears when the observer's line of sight crosses a fan-shaped plane of particles that trail along the comet's orbit. It's a kind of projection effect, but the scale and clarity of the sunward feature in the Hubble data are striking. If geometry explains it, the specifics must be just so. If geometry fails to capture the full effect, then we may be looking at a jetting pattern or dust grain behaviour that concentrates material into tight, forward-directed structures. Such a pattern could arise from vents aligned with the subsolar point, or from the way certain mid-sized grains respond weakly to radiation pressure, hugging the orbital plane and stacking into a bright sunward spike. In the undercurrent, some have wondered, quietly, carefully, about non-natural contributions. It is not an accusation so much as a laundry list of anomalies. The alignment with the ecliptic, the composition skew, the colour switch, the brightness law, the antitail. Stack them, and coincidence starts to feel heavy. But extraordinary claims carry an even heavier burden. The tools of ordinary physics are far from exhausted here, and every step forward, each new image, each refined spectrum, rewards patience by ruling out the alluring and untrue. On the chemical front, the story keeps gaining threads. Observations from large telescopes flagged cyanide and nickel production rates rising with a slope around 9 on a log-log plot, one of the steepest ramp-ups charted in comet science. Nickel without iron, showing up out of proportion to familiar mixtures, is another curiosity. On Earth, human metallurgy often pulls nickel without its usual iron partner, but nature can do odd mixings too, especially in environments we don't often sample. It's a detail to hold lightly for now, neither dismissed nor overplayed. A separate analysis of the coma's bulk composition points to a dominance of carbon dioxide by mass, with carbon monoxide a strong second and water trailing. That ratio marks Atlas as chemically distinct from many solar system comets and even from the previous interstellar visitors. It's an echo of the formation field in which Atlas congealed, colder perhaps, or shaped by a different pattern of early stellar winds and radiation, or born from materials with a different metal pore heritage. every percentage in that breakdown is a breadcrumb to a nursery we've never seen. The cyanide growth curve remains especially intriguing. CN radicals are common in comets, but their production typically follows gentler rules. A ninth power law suggests a behavior that switches on like a cascade. Fractures meet fractures, pathways meet reservoirs, and the release multiplies on itself. It could be chemistry at work in the coma itself, where sunlight breaks apart parent molecules more efficiently as the cloud thickens. Or it could be structure inside the nucleus, a labyrinth of pores and ices that becomes percolation ready only when the comet crosses a thermal brink. The calendar brings its own tide. On the 3rd of October, Atlas will slide past Mars at roughly 28 million kilometers, a neighborly visit by interplanetary standards. From the red planet's orbit, Europe's Mars Express and the ExoMars Trace Gas Orbiter will try to pull spectroscopic threads from the faint light to chase a line or two that Earth's air and geometry keep hiding. Their cameras, built for deserts and canyons, will do their best as celestial instruments. Meanwhile, NASA's rovers, tuned to chemistry a few inches from their wheels, will continue sniffing their own thin sky. If any dust or gas from Atlas changes the Martian air in a measurable way, it would be a lovely accident of timing. Further out, November brings a chance, slim but real, for ESA's Jupiter Icy Moons Explorer to contribute. Its instruments are tailored to the ultraviolet shimmers of icy worlds and magnetospheres, but they might catch spectral echoes from the comet, offering angles Earth can't. Coordinating those attempts with NASA's Europa Clipper could, in the best case, yield a stereoscopic glimpse of the coma's texture. Practical constraints remain: spacecraft thermal strategies, antenna use, data rates. If anything is captured, the packets may drift home slowly. That is the pace of deep space. It is worth circling back to the second comet misunderstanding that has cast a long, excitable shadow over these weeks. Comet Bernardinelli-Bernstein, often labelled C2014 UN 271, is indeed enormous, with a nucleus on the order of 100+ kilometers across. But its timeline is measured in slow arcs. Its perihelion won't arrive until 2031, and even then it will keep its distance beyond Saturn's path. The ALMA array has mapped carbon monoxide jets rising from it, revealing asymmetries that tell a tale of an irregular, rotating giant, but nothing in that story implies a sudden incursion into the inner solar system. It is a different drama entirely. The viral mashup comes from the human tendency to braid news together. Untangling that braid returns clarity. There is Atlas, here and now, surprising us daily. There is Bernardinelli-Bernstein, vast and far, surprising us slowly. Another strand being tugged is Origin. A team led by Xavier Perez-Couto has tried to rewind Atlas's path through the galaxy, turning the sky's current into a kind of backward-running river. 10 million years of gravitational influence can be modelled with caveats, but the output didn't point cleanly to a single star system. The longer an object drifts between suns, the more times its course is nudged by stars, clouds, the batwing tug of spiral arm gravity, until the line back to a birthplace is fog. One hypothesis pins Atlas to the population of the thick disk, older stars with lower metallicity, where conditions would have been different at birth. If so, the comet becomes more than a traveller. It becomes a time capsule carrying chemistry from an era not much represented in our local sample. The pre-discovery trail adds to the feeling that we're tracking something apart. In TESS images from May 2025, 2 months before discovery, Feinstein's team teased out a faint, fuzzy smudge and confirmed it as Atlas, already active. That takes skill and patience, stacking exposures, scraping away starlight, coaxing a whisper from the background. Zwicky Transient Facility data pushed the activity timeline back further still, into March, where small brightness variations matched the pattern of low-temperature volatiles waking. The brightening rate, fit with a power law, came out steep, steeper than the interstellar comet Borisov wore, more like the slopes seen in comets that have followed the sun's glow a few times already. And we return again to the green chemistry puzzle because it sits like an emerald at the center of everything. Diatomic carbon is the traditional culprit behind that glow, its photons flaring in the ultraviolet and visible bands when sunlight excites the molecule. But the way the green switched on so suddenly suggests either that the inner layers passed a thermal tipping point or that structural disruption brought reactants together at last. When a comet's interior fractures, pathways open, trapped pockets connect, and chemistry that was once impossible becomes routine. Another path, still plausible, is that Atlas hosts a fluorescent molecule we rarely see in comets from our system, a species that lights up under specific transient conditions and then fades when the conditions change. The timing matters. The transformation arrived as solar input climbed, consistent with heat-driven activation, but too abrupt to be called a gentle thaw. Thresholds often produce that kind of cliff. A certain pore size is reached, a crystalline ice crosses its glass transition, a vent roof collapses, and a new regime begins. If you've ever watched frost give way to streaming water on a winter gutter, you know how sudden such changes can appear after days of incremental warming. As if to add one more layer of oddity, polarimetric measurements have flagged an unusually deep negative polarization, around -2.77%, with a low inversion angle near 6.5 degrees. Polarization is a way of reading the shapes and sizes of dust grains, the way their surfaces scatter light. Numbers like these sit at the far edges of comet profiles we've catalogued. They whisper of grains with unusual geometries or coatings, perhaps bright, perhaps ordered, perhaps altered by a long cold crossing through interstellar space. The dust could be sheathed in organics or shaped by crystalline growth we don't often sample locally. Polarimetry doesn't give you a photograph of a grain, but it does give you a silhouette, and this silhouette is strange. Collect all these traits in one place: the composition ratio that exalts carbon dioxide, the early activity, the rapid climb in CN, the polarization oddity, the sunward feature, and Atlas feels less like an outlier and more like the first clean example of a class we haven't yet defined. Naming that class will take time, repeated observations, and eventually another interstellar visitor that shares the pattern. Finally, Hubble's relentless gaze has tried to pin down the nucleus itself. Estimates have bounced between a few hundred meters and several kilometers, roughly 440 meters up to around 5.6 kilometers in diameter. That wide bracket reflects how hard it is to separate the pebble from its fog. The coma's light wraps the nucleus, and unless you can peel the layers cleanly, you end up attributing some fog to the rock or some rock to the fog. The choice of size matters. A small nucleus that bright would imply an engine working at ferocious efficiency. A larger nucleus would give you more mass to work with, more ices to vaporize, without requiring such extreme efficiencies. Either way, spectra suggest the nucleus is dark, a surface that turns most sunlight into heat and keeps only a sliver for reflection, reflecting only a small fraction of incident sunlight. 3I Atlas is darker than you might expect. So dark, in fact, that even bright sunlight slips across it like water over basalt. That low reflectivity could have a few origins. It may be the patina of complex organics, baked and rearranged by radiation during the long, cold drift between stars. It may hint at a carbon-rich recipe, a chemical inheritance from a natal system unlike our own. Or it could be the scar tissue of space weathering, countless micrometeorite pings, thermal shocks, and charged particle sandblasting that gradually rewrote the surface as the comet wandered the deep. Pair that darkness with the uncertainty in the nucleus size, somewhere in a wide band rather than a neat single number, and the puzzle thickens. Big and dark behaves differently than small and dark. Both tell different thermal stories. Untangling which is which will require careful heat flow models that blend many colours of light and many lines of sight, especially as Atlas climbs toward peak activity around perihelion. Its activity profile has been strange from the start. Atlas began to stir far from the Sun, switching on at distances where our homegrown comets stay asleep. That early awakening points toward ices that vaporize at lower temperatures. Carbon dioxide and carbon monoxide taking the lead while water remains locked away. The brightening itself follows a notably steep curve. Fit the data with a power law and you get a slope around -3.8, a number more, at home among old comets that have threaded the inner solar system multiple times and carved efficient channels for their gases. But Atlas is a traveller from elsewhere, likely on its first close pass by any star in a very long time. Fresh in provenance, veteran in behaviour, that contradiction demands an explanation. Either it formed under unfamiliar conditions that mimic the handiwork of repeated solar visits, or the long interstellar cruise quietly modified its structure into something that behaves, optically and thermally, like a seasoned object. Zoom in on the chemistry and the responsiveness gets dramatic. Measurements of both dust and gas show production rates that surge as the comet draws closer to the Sun, with some species ramping according to power laws with exponents near 9. That kind of curve doesn't just rise, it vaults. A response so sensitive suggests volatile reservoirs lurking just beneath the skin, easy to heat and quick to vent, or an interior that moves heat around efficiently, pores connecting to pores until the nucleus becomes a network, not a block. To catch these changes from every angle, a small armada is watching. Throughout late September into early November, NASA's Parker Solar Probe, built to sip the near-Sun environment, will open its wide-field imager and watch Atlas against the coronal glow. Few observatories can offer a vantage so close to the furnace. Out nearer the Trojan highways, the Lucy spacecraft may manage a look of its own, adding an outer system perspective. And in early September, as it cruised toward a metal world, NASA's Psyche passed near Atlas's path. If any snapshots were taken, they've yet to be shared. Perhaps the most tantalizing possibility lies with ESA's Hera mission. Its cameras and spectrometers were designed to dissect an asteroid's surface in exquisite detail, but the same sharp tools could, if geometry and timing cooperate, sketch the nucleus of an interstellar comet with a clarity we've never had before. Imagine seeing not just the glow, but the contours. Every one of those observing plans has to navigate the realities of deep space logistics. ESA's JUICE spacecraft, splendidly placed for a unique view during peak activity, has been flying a trajectory that forces it to use its high-gain antenna as a thermal shield when it draws near the Sun. With the big dish pointed at the heat, downlink rides on the smaller backups, and data rates tumble. The result? Even if JUICE catches something remarkable, the packets may trickle home slowly, possibly not arriving until early 2026, when the comet has already faded into memory. NASA's Europa Clipper, threading its own path through the inner system, faces a similar tug-of-war between instrument design and opportunistic comet science. Its ultraviolet spectrographs could still prove invaluable, sniffing out lines that Earth's atmosphere hides, but coordination will be key. Observation windows are brief. Geometry shifts quickly. The spacecraft that can help must do so on tight schedules and tighter bandwidth. Underneath the logistics is a deeper tremor: theory. Atlas stacks anomalies in a way that nudges at our assumptions. Its path through the sky, its unusual chemistry, the steep brightening, the sudden green turn, the improbable sunward feature. None alone overturns a field, but together they ask whether we're looking at a new category of interstellar wanderer, born under conditions our neighborhood rarely reproduces. A CO2-heavy makeup, an eagerness to outgas in the cold, an unusually dark skin and uncertain bulk. These point to formation around stars with different element budgets, perhaps in environments common to the galaxy's thick disk. If true, Atlas is not just a messenger from afar, it's a messenger from an earlier chapter of the Milky Way, carrying the chemical handwriting of young, metal-poor stars. There are more conservative readings, of course. Nature is generous with oddities that don't require rewriting the laws. Geometric projection can turn dust sheets into sunward spikes. Grain sizes that respond weakly to radiation pressure can stack brightness where we don't expect it. Thermal fracturing can flip chemical switches in abrupt, threshold-like ways. Still, the alignment of quirks is enough that some researchers are at least entertaining broader possibilities about what comet might encompass. October is the pivot. Around the 13th, Atlas will reach perihelion at roughly 1.44 astronomical units, wedged between Earth's lane and Mars's. That is the moment of maximum solar push, the time when outgassing roars, when jets sharpen, when the interior's architecture most strongly declares itself. Unluckily for ground-based observers, this peak arrives during solar conjunction. From Earth, the comet will sit too near the Sun to separate safely in the glare. The most transformative hours may pass behind daylight's curtain for us, which is why the space-based eyes matter. Parker Solar Probe, purpose-built for the furnace, may provide the only detailed look right at the crest of activity. After that crest, the story shifts from ascent to return. Post-perihelion, as November dawns and the comet pulls away from the Sun, we'll get a second act: cooling, settling, and whatever changes the heat has wrought. Some comets crack or peel, shedding fragments under stress. Others develop new vents and keep them for months, even years. Watching which path Atlas takes will tell us about its toughness, its layering, its plumbing. If the brightness curve relaxes in new ways, if the spectrum drifts, if the coma's texture changes, those are fingerprints of interior structure. And then, steadily, the glow will diminish. By early 2026, Atlas will likely be too faint for all but the largest instruments, a memory slipping back into the dark between stars. It won't return. Whatever it learned here, whatever trace of solar wind it carries, whatever flecks of interplanetary dust, whatever isotopes whisper of our neighborhood, will travel outward for millions of years. The idea of contamination is mostly poetic in this context, but not entirely. The comet will be lightly salted with our sun's particles, with motes from our dust lanes. In the most speculative corners, people even wonder about the vanishingly small chance of biological hitchhikers from Earth's highest air, though space is a hard filter and such survival is exceedingly unlikely. More plausible is the imprint of our technology in subtle isotopic patterns, ghostly signatures that, if ever measured by someone else, would say that a civilization once touched this region. The questions that Atlas raises won't end when its light fades. How often do visitors like this cross our path? Are they rare, or are we just now learning to see them? If they are common, then the galaxy is a web of exchange, atoms and molecules, ices and dust, woven across huge distances and timescales. The quirks in Atlas argue that, interstellar object is a broad category, not a narrow one, and that each guest brings a different biography. Coming surveys will do the counting. The Vera Rubin Observatory, with its deep, wide, fast cadence, is poised to flood our schedules with new alerts. A dozen interstellar visitors a decade is within reach. With numbers come patterns, and with patterns, the ability to separate the truly extraordinary from the merely unusual. That flood of detections won't just be catalogue entries. ESA's Comet Interceptor mission is a sign of a new approach. A spacecraft on standby, ready to sprint when a suitable target appears. Rather than planning the mission for the comet, we'll plan the comet for the mission. Meet the visitor on its own terms. Future concepts go further. Quick launch interceptors that can snap spectra at short notice. Eventually, perhaps, sample returns that would deliver dust from another star system into our laboratories. Getting there requires sharper tools, and those tools are arriving. Spectrographs continue to push toward finer resolution. Algorithms trained on oceans of observations are learning to spot the subtle, the off-trend, the pay attention to this. Space telescopes to come, successors to JWST, will carry coronagraphs that make it easier to watch small, faint bodies near the sun's glare. Quantum-level sensors, better materials, faster models, each advances our reach a little further. It's not hard to imagine an analysis pipeline that flags unusual composition follow up immediately, within minutes of a discovery alert. Underpinning the instruments is the humbling philosophy of the thing. We live in a system that breathes with the galaxy, not a sealed terrarium. Material arrives, material leaves. Interstellar objects force us to accept how small a slice of the cosmic story we usually see. For a handful of weeks or months, one of those stories passes close enough to read, and we elbow against our limits trying to catch every line. It is tempting to leap to extraordinary interpretations, artifacts, engines, intention, but the honest path is patience and evidence. Atlas likely remains a natural object doing natural, if uncommon, things. Wrestling with that likelihood while keeping one's mind open to surprises is the balance science asks of us. None of this happens in isolation. Atlas has been a global project by default. Telescopes in Chile, South Africa, and Hawaii scanning the sky every night. Automatic alerts hammering out discovery notices within minutes. Radio arrays listening. Optical observers tracking. Ultraviolet instruments peering from above the air. Space-based giants choreograph with one another. JWST and Hubble weaving multi-wavelength coverage, and amateurs thread the needle between the giants, nimble enough to catch the first breath of green that the surveys might miss. Citizen networks like Unistellar fold thousands of small observations into a single, powerful dataset. The practices pioneered here, standard formats, rapid notifications, shared calendars, are the scaffolds we'll use for the next visitor and the one after that. Behind the telescopes and antennas, the computers strain. Each clear night spills terabytes of raw data that must be calibrated, cleaned, and compared. Machine learning models comb through light curves and images, searching for correlations a tired human eye would miss. Subtle shifts in polarization, tiny kinks in a brightness slope, a faint change in coma texture that precedes a jet. Teams run magneto-hydrodynamic simulations to see how outgassing couples to the solar wind, how the comet's ion tail might twist under the interplanetary magnetic field. Supercomputers churn on plume dynamics and dust grain charging, and in a different set of models, celestial mechanics gets the last word. Rewind the orbit through the galaxy's gravities, stars, clouds, the galaxy's own tide, and trace Atlas's path back millions of years, accounting for each nudge and whisper from passing suns during its interstellar journey. 3I Atlas is darker than coal under starlight, so dark that sunlight seems to slide off its skin rather than shine back toward us, that low albedo may be the varnish of complex organics cooked by radiation during eons in deep space, a carbon-rich surface inherited from a very different kind of stellar nursery, or weathering scars laid down by micrometeorite pings and solar particles over a journey measured in millions of years. Pair that darkness with the wide uncertainty in nucleus size, and the riddle deepens. A small, very dark body must vent furiously to create what we see, while a larger, equally dark body could supply the same glow with steadier means. The only way to sort those possibilities is with careful thermal modelling that knits together many wavelengths and many viewing angles, especially as Atlas climbs toward peak activity near perihelion. Its activity curve tells a different kind of secret. Atlas woke early, far from the sun, at distances where homegrown comets stay asleep. That points to ices that vaporize at lower temperatures than water does, carbon dioxide and carbon monoxide stepping onto the stage, while H2O remains locked beneath the crust. Fit the brightening with a power law and you get a steep slope near 3. 8, a number that usually belongs to dynamically old comets from the Oort cloud that have threaded the inner solar system many times and carved efficient pathways for heat and gas. But Atlas is not local and not experienced in that way. Fresh traveller, veteran behaviour, the mismatch begs for an explanation. Either it was built under conditions that mimic the effects of repeated solar passes, or its long interstellar trek rearranged the interior into a network that behaves like a seasoned comet when warmed. Look closer, and the responsiveness is extreme. Dust and gas production do not merely increase as solar distance shrinks. For some species, they climb with exponents approaching 9. That is a volt, not a stroll. Such hypersensitivity implies volatile layers, only a thin skin below the surface, or a nucleus that ferries heat inward with unusual efficiency, where pores connect to pores until warmth races through the interior and new vents switch on in cascades. To understand a shape you can't touch, you watch it from many angles. Across the solar system, spacecraft are getting ready, or already trying, to do exactly that. Parker Solar Probe, built to fly in the furnace, will aim its wide-field imager between late September and early November, offering a near-sun vantage no other observatory can match. Farther out, Lucy may steal a look from its Trojan-bound path, and Psyche, on its way to a metal world, passed near Atlas's lane on the 4th of September. If it snapped any frames, we haven't seen them yet. ESA's Hera mission, designed to dissect the aftermath at the Didymos system, could, if the geometry turns kind, apply its sharp instruments to Atlas, sketching surface and structural hints with a clarity we have never had for an interstellar comet. All of those plans collide with the realities of deep space navigation and bandwidth. JUICE, splendidly placed for a unique perspective during peak activity, must use its high-gain antenna as a heat shield when it draws nearer the sun. That forces downlinks through small backups and throttles data rates. Even if JUICE catches something spectacular, we may not see the bits until early 2026, long after the show has faded. Europa Clipper travels its own careful path. Its ultraviolet spectrographs are tuned for icy moons, but might still taste emission lines from the comet, if timing and pointing allow. Coordinating windows that shift by days and hours is a quiet ballet. The choreography must account for distance, geometry, and the finite stream of data each spacecraft can send home. While the logistics unfold, the theory is already bending. Atlas stacks anomalies in a way that makes us ask whether we're looking at a new category of interstellar wanderer. a CO2-heavy composition, eagerness to outgas in the cold, a low reflectivity skin, a brightening law at the steep end, a sudden swing from red to green, and that sunward extension of light. No single piece overturns comet science, but together they pull at the frame. One interpretation ties Atlas to older stellar populations in the galaxy's thick disk, where element abundances and radiation fields differ from our Sun's neighborhood. If so, this is not just a visitor from afar. It is a visitor from an earlier chapter in the Milky Way, carrying chemistry set by stars that lived fast and left a different mix of materials behind. There are humbler readings too. Geometry and projection can stack dust into apparent sunward features. Certain grain sizes feel radiation pressure weakly enough to cluster along the orbital plane and brighten the wrong direction. Thermal cracking can flip chemical switches abruptly when thresholds are crossed. Still, it's the combination that keeps curiosity awake. October will be the hinge. Around the 13th, Atlas will reach perihelion at roughly 1.44 astronomical units between Earth and Mars, precisely when the Sun's hand is heaviest. That is when vents roar and the nucleus reveals its architecture most plainly. From Earth, though, it's a bad showtime. Solar conjunction hides the comet in daylight glare, making our largest telescopes nearly useless for the week or two when the action is most intense. Space-based observers will carry the load. Parker Solar Probe, living where the heat is, may give us the only detailed look right at the crest. After the crest, the story turns outward. As November arrives and Atlas emerges from conjunction, we'll watch cooling and change. Some comets split under stress, shedding shards that drift like glowing embers. Others shift into new outgassing patterns that persist for months. Which path Atlas takes will sketch its strength and stratigraphy. If its light curve relaxes differently than it climbed, if the spectrum drifts toward new lines or away from old ones, if the coma's texture softens or grows filamentary, those are all clues to plumbing we cannot see. And then, as surely as night follows day, the glow will dim. By early 2026, the comet will likely slip beneath the reach of most instruments, returning to the wider night between stars. It won't be back. Whatever it has picked up here, solar wind particles, interplanetary dust motes, faint isotopic whispers of our corner, will ride along. The prospect of biological hitchhikers from Earth belongs more to imagination than to probability. Space is too harsh and the odds are too long. But industrial isotopic fingerprints and manufactured molecules do exist in our environment, and in principle some could adhere to a passing surface. If Atlas ever drifts near someone else's instruments, those signatures would mark that a technological species once breathed in this part of the galaxy. The questions Atlas raises are bigger than a single visit. How often do we host travelers like this? If the answer is often, then exchange between star systems is not a poetic notion, but a quiet, constant fact. Material flows through the Milky Way's lanes, carrying chemistry and perhaps prebiotic complexity across enormous distances and times. Atlas's quirks argue that interstellar object is a wide box with many compartments. Coming facilities will do the counting. The Vera Rubin Observatory's fast, deep cadence should multiply discoveries, pushing us from case studies towards statistics. With numbers come patterns, and with patterns come tests we can trust. Those tests won't be confined to telescopes. ESA's Comet Interceptor is a promise to be nimble, a spacecraft waiting in the wings for the next pristine target, possibly an interstellar one, to appear with little warning. Farther ahead, rapid response concepts imagine pre-positioned craft and high-efficiency propulsion poised to chase the next visitor, maybe even bring a sample to Earth. The difference between spectra gathered from far away and grains studied in a lab is the difference between a song heard through a wall and the instrument in your hands. Technology is the quiet engine making that leap possible. Spectrographs gain sensitivity and stability. Algorithms trained on oceans of data learn to spot the subtle shift, the out-of-family line, the morphological quirk that says follow up now. Future space telescopes with advanced coronagraphs will watch faint bodies nestled near the sun's glare. Quantum-grade sensors, better thermal control, faster modelling, all of it expands what we can see and how quickly we can turn seeing into understanding. The philosophy underneath is simple and humbling. We live in a system with open windows, not sealed doors. Material crosses our threshold, leaves again, and the galaxy's weather writes on our sky. Interstellar visitors remind us how small a slice of the story we typically capture. For a few weeks or months, we read a page as it flutters past. It is tempting to leap to extraordinary explanations, but the honest path is patience, measurement, and models that earn their claims. Atlas likely remains a natural object doing natural, if uncommon, things. Holding that likelihood while staying open to what we do not yet know is part of the discipline. If these deep, unhurried journeys through space science help you relax, consider liking and subscribing to Space Historian so you don't miss the next chapter. None of this would be possible without a web of observatories working together. Telescopes in Chile, South Africa, and Hawaii scan the sky in a nightly rhythm. Automated alerts distribute discoveries in minutes. Radio arrays listen while ultraviolet instruments float above the air. Space-based giants coordinate multi-wavelength coverage, while dedicated amateurs, nimble, persistent, often catch the first hints of change, as they did with Atlas's green turn. Citizen networks stitch thousands of small observations into a contiguous story. The data standards, notification protocols, and shared calendars forged during this campaign are the scaffolding we'll use again and again as more interstellar guests arrive. Behind those domes and dishes, the computation hums. Every clear night drizzles terabytes of raw images that must be calibrated and compared. Machine learning tools comb light curves and spectra for patterns humans might miss. Tiny kinks in a brightness slope, faint asymmetries in coma shape, whispers in polarization that predict a jet's birth. Magnetohydrodynamic models try to capture how outgassing tangles with the solar wind and interplanetary magnetic field. Supercomputers churn on plume physics and dust charging. Celestial mechanics rewinds orbits through the galaxy's gravitational halls, past field stars, clouds, and spiral arm tides, to infer where Atlas most likely came from. Those backward integrations don't find a neat return address. Instead, they outline a handful of probable regions and emphasize just how uncertain ancient paths can be after countless small tugs. Observations feed those models, the models guide the next observations, and a feedback loop emerges that sharpens our grasp of comet physics, galactic dynamics, and the properties of the space between stars. Each new measurement hems in some possibilities while revealing others we hadn't considered. The isotopic riddles are among the most alluring. With high-resolution spectroscopy, we may one day read the fine ratios of isotopes in Atlas's gases, the fingerprints of the nuclear furnaces that forged its atoms. Different stellar masses and life cycles leave characteristic isotopic patterns, and the current carbon-to-nitrogen balance in the coma already hints at conditions unlike those that shaped most of our local comets. The challenge is technical. Atlas is faint, it moves, and exposure times are short. Better stability and sensitivity from future space-based spectrographs could change the game, testing models of galactic chemical evolution with a directness we've never had. In the most breathtaking scenario, we might find ratios that do not fit any known stellar process, forcing either new nuclear physics or formation stories beyond our present frameworks. Heat will write its own chapter soon. As Atlas approaches perihelion, thermal models attempt to forecast how sunlight will creep into the nucleus, which layers will wake first, and how the crust will respond. Early activation hints at very low thermal inertia, or a composition rich in volatiles that don't need much warmth to escape. Subsurface temperature profiles dictate when each molecule crosses its sublimation threshold, and the steep activity rise suggests either rapid heat penetration or volatile pockets lying just beneath the surface. Simulations that match the changing brightness and spectrum tend to prefer a layered interior, with different ices residing at different depths, a stratigraphy that could date back to formation or have been sculpted during the long cold drift between stars. The abrupt colour shift from red to green fits neatly into that picture. A threshold crossed, a crack opened, and chemistry once hidden stepping into sunlight. All of this unfolds within a magnetic sea. The solar wind carries an embedded magnetic field that threads the comet's coma. Charged dust and ions feel those lines and twist along them, sometimes building asymmetries or preferred flows that match the field's orientation at that moment. Features that look odd in a static picture may be the natural language of plasma and dust. Parker Solar Probe, which measures the wind and magnetic field in exquisite detail, could catch signatures of Atlas's interaction during the close pass. Ripples in the flow, subtle changes that mark where the comet's breath pushes back. Spread across the solar system, magnetometers on other spacecraft provide context, letting us see how a small disturbance propagates through a vast medium. The models that chase those effects, full plasma simulations with chemistry, are hungry for computing power, but promise predictions we can test. Dust adds another layer of intrigue. Polarization measurements for Atlas sit far from the usual comet family, hinting at grains with shapes, coatings, or compositions uncommon here. By modeling how different particles scatter light, researchers try to reproduce the deep negative polarization observed, a clue that grains may be intricate aggregates, bright-skinned, crystalline, or something stranger. Radiation pressure tugs on those grains in ways that depend on size and composition, shaping the coma and tail. Charged dust meets magnetic fields, and the choreography grows richer, potentially explaining sunward features and asymmetric fans that classic models struggle to capture. Spectra evolve as the comet warms. What started as a CO2-dominated signature has picked up complexity as new molecules reach their activation temperatures. The steep rise in cyanide production is one example. Others will follow as layers open. High-resolution line profiles reveal outflow speeds and directions, helping us sort between diffuse venting, narrow jets, and colliding plumes. The sudden green glow, whatever molecule precisely drives it, deserves that watchful attention. A slow, steady drift through perihelion and into the outbound phase will give us a moving laboratory in which to test how interstellar material learns to behave under a new star's light. With heat comes risk. Comets fracture. If internal stresses outrun mechanical strength, Atlas could shed pieces or even break apart. Early outgassing may already have opened weaknesses that the perihelion pulse will exploit. Detecting fragments demands both angular resolution and clever processing, separating tiny moving points from the shimmering background. Hubble would be the best eye for such a task, but the timing near the Sun complicates things and could hide the most dramatic moment. A breakup would rewrite the script. Multiple faint targets to study, lower signal from each. A debris ribbon that maps the nucleus's interior more honestly than any intact surface ever could. Beneath the visible changes lie the engines that drive them, and those engines are not yet fully described. Surface sublimation alone cannot explain the early activity. Something about Atlas either transports heat and gas with remarkable efficiency or leans heavily on species more volatile than water ice. Subsurface sublimation that feeds gas through porous networks could account for some features if the interior is a sponge of specific pore sizes and pathways. Elsewhere, explosive outgassing sparked by phase transitions or chemical reactions might be at work, producing the sharp brightness jumps we've seen. The sunward extension, a luminous tether in seeming defiance of radiation pressure, still asks for a better framework. Directed jets shaped by topography, dust grains with unusual charge-to-mass ratios, or projection effects under just so geometry are all on the board. As the catalogue of molecules grows, each new line pins another point on the map of Atlas's origin. Water, CO2, Colorado, CN, and an array of organics draw a picture that diverges from most solar system comets. The heavy lean toward carbon dioxide is the loudest note. Trace species push our instruments to their limits. Absences can be as instructive as presences, underscoring what the natal cloud lacked or what the long journey and recent heating have erased. Laboratory ice experiments, radiation baths, temperature cycles, mixed grain matrices translate those spectral hints into history, telling us which environments make which molecules and what happens to them across cosmic time. The nucleus itself, hidden in its own glow, remains the hardest thing to know. Density, porosity, layering, and strength must be inferred from rotation, outgassing patterns, and the way the coma responds to sunlight. Different internal layouts can reproduce similar observations, and whittling the list down requires more constraints. A secure rotation period would help, but reading it out of a faint, rapidly changing light curve is difficult at best. Long baseline photometry may yet tease it out. The odd polarization values point to surface textures and compositions that diverge from what we're used to seeing on local nuclei, hinting at either exotic materials or familiar materials arranged in unfamiliar ways. All those fingerprints point backward to a birthplace. If Atlas formed where carbon outpaced oxygen and metal content ran low, if its star's winds and radiation sculpted grains differently, then its present chemistry is a memory of that distant sky. Isotopic ratios, especially once measured well, will be our best direct evidence of stellar nuclear processes in the parent system. The likely age, billions of years, means the comet records conditions from a time when the galaxy's chemical mix was not the same as today's. Comparing Atlas with other interstellar visitors and with our own comets will tell us whether we're seeing a common extragalactic dialect or a rare accent now almost extinct. Trajectory work tries to turn the present path into a history. Detailed calculations thread the comet's motion backward through millions of years of galactic gravity, testing which regions and which stellar populations fit best. Right now, the alignment with the galactic plane and the kinematic hints point toward the thick disk rather than the thin disk where the Sun resides. Along the way, close stellar passages would have nudged the course again and again, smearing out any clean return address. Statistical methods can still flag likely neighbourhoods even when a specific star remains out of reach. Atlas's high speed relative to the Sun suggests either a quick kick at ejection or a series of gravitational assists during its long wander. Better astrometry in the coming months will refine the parameters and tighten those inferences. Whatever the final answers, the observing campaign itself is already a legacy. Archival surveys that captured Atlas before anyone knew to look proved their worth. Wide-field programs that watch the whole sky every clear night showed why they matter. The partnership between professional facilities and dedicated amateurs extended coverage across time zones and weather, filling gaps no single observatory could cover. Standardized formats, rapid alerts, and coordinated schedules wrung the most science out of a short window. The lessons now feed directly into the design of next-generation surveys and the playbooks for spacecraft opportunism. On the theory side, Atlas is stress-testing our models. Classic sublimation pictures built around water ice don't survive contact with early activity and rapid brightening. Sunward scattered light strains our dust dynamic shortcuts. The response is already taking shape. Multi-component, three-dimensional models that mix chemistry, porosity, charging, grains of many sizes, and nuclei with real topography. They are expensive to run but necessary to capture the full behavior we're seeing and to prepare for the next interstellar object that refuses to behave like a local. Detection statistics hint at just how many of those objects we're missing. 3 confirmed interstellar visitors within 8 years implies a reservoir far larger than our current count. As new surveys come online, the sensitivity floor will drop and the rate will rise. Population models extrapolate from what we've caught to estimate how many pass through annually, how big they are, and how active they tend to be. So far, our sample is biased toward the big and the bright. Better instruments will tell us whether the small ones follow the same distributions we see in our own comet and asteroid families, or whether interstellar space sculpts them differently. Mission planners feel the squeeze of time most acutely. Discoveries arrive with days or weeks of notice, not years. That is why standby architectures matter. Comet Interceptor points the way, waiting to sprint towards whatever suitable target appears. Concepts under study imagine pre-positioned spacecraft, fast propulsion, and streamlined approvals so we can launch within months. The payoff would be transformative. Internal structure measured directly, chemistry mapped at the source, perhaps even a sample jar that opens in a terrestrial lab. And through it all, the public has been listening. Atlas's strange chemistry, early stirring, green shimmer, and sunward glow make a narrative that feels both scientific and human. It is a mystery told in spectra and light curves, but also a lullaby of long travels and hidden interiors. People lean in when the universe does something unexpected, and this comet has done exactly that, inviting curiosity from seasoned observers and first-time skywatchers alike. The combination of genuine unknowns, potential implications, and striking imagery draws a wide circle. Teachers, students, hobbyists, night shift workers, insomniacs, and holds them gently in the shared quiet of a story still being written, resonating with diverse audiences. Social media has been both the wind at Atalus's back and a cross-current tugging it off course. In the rush of posts and stitches and reels, careful measurements share space with wild claims and polished speculation. A sober nuance can be drowned out by a dramatic thumbnail. You've seen it yourself. The second comet story blooming from a seed of confusion, an earnest tangle of timelines and names amplified by algorithms tuned more for emotion than for truth. In that stream, distinguishing a genuine discovery from a viral mirage takes patience and source checking, a slow breath before the share button. And yet there's a brighter side, because 3i Atlas isn't just news, it's a bridge. Its interstellar passport turns abstract ideas, galactic chemistry, stellar evolution, the long traffic of small bodies between suns, into something you can picture. Teachers seize it for lessons. Curious night owls dive down the rabbit holes. Interest crystallizes into support, and support sometimes shifts the gentle levers that decide which missions fly. If curling up with these deep space stories helps you unwind, you're welcome here. And if you want more of them, consider tapping like and subscribing to Space Historian. It keeps these quiet explorations drifting your way. Atlas is also a showcase for how quickly our tools are changing. Each year brings another lens polished sharper, another detector cooled a little quieter. Spectrographs, once too insensitive, now pluck emission lines from objects so faint that older instruments would have seen only noise. That matters most at the edge of possibility. Far-out visitors like Atlas beginning to stir when they're still dim and distant. Machine learning systems, trained on oceans of archival images, learn to spot patterns we would miss. The faint asymmetry in a coma, the tiny kink in a light curve that hints at rotation or outburst, the spectral ratio that whispers, "Follow up now." And beneath the eyepieces and dashboards, computation is our second telescope. With faster models, we stitch physics together. Heat flow and chemistry, dust charging and radiation pressure, magnetic fields threading gases, to keep theory breathing in step with what new instruments reveal. The real magic happens when we weave ground and orbit into one tapestry. A space telescope's clean, airless spectrum dovetails with a mountaintop observatory's long nightly cadence. A solar probe's plasma measurements set the stage for a narrowband images snapshot from Earth. Each platform sees a different slice of the story. Together they write a chapter no single instrument could tell. Atlas needs that chorus. It moves quickly, fades and brightens, changes texture as it warms. No single vantage can keep pace, all of which primes us for what comes next. If Atlas can be this strange, then the next interstellar visitor may bring surprises of its own. With new survey systems about to open their eyes, we won't only catch such objects closer in, we'll spot them farther out, weeks or months earlier. That extra breathing room is more than convenience. It's the difference between a hurried glimpse and a careful study, between we saw it and we understood it. With time to plan, spacecraft can pivot and point. Interceptor missions, waiting like sprinters in their starting blocks, can leap. As the catalogue grows, statistics will begin to speak. Correlations between chemistry and speed, between polarization and activity, between origin clues and orbital geometry. From those patterns, we'll tease out common threads, formation rules that operate not just here, but across the galaxy. Future space telescopes will deepen the palette, higher sensitivity, steadier baselines, and spectrographs that separate faint lines crowded together like whispers in a choir. That's where isotopic measurements will bloom, from the rough outline we can draw today to the fine-grained fingerprints that tell us about nuclear forges in other suns. And as rapid response spacecraft mature, we'll go from a handful of snapshots to full portraits. Chemistry mapped in 3 dimensions, dust dynamics filmed in motion, interiors inferred by how the surface breathes. The goal is simple to say and vast to achieve, not just to see interstellar visitors, but to truly know them. To place Atlas in its proper frame, zoom out to the galaxy itself. Think of it as one pebble from a beach you'll never walk, flung into the cosmic road by the tides of planetary formation. If its age runs to billions of years, as seems likely, then it has seen the Milky Way's chemistry evolve, felt the gravity of stars that have long since dimmed. Its mixture of ices and grains preserves the memory of a stellar nursery with a different element budget than ours, perhaps older, perhaps harsher, certainly distinct. Compare Atlas to the 2 interstellar objects we've already met, and to our homegrown comets, and you begin to see not a single script, but an anthology. Each small body is an experiment. Different starting materials, different temperatures and pressures, different radiation baths and collision histories. The hint that Atlas's path aligns with the thick disk points to an ancient population, a first tangible sample from that older stratum of the galaxy. If future studies show consistent differences between thick disk visitors and thin disk cousins, we'll have in our hands a new way to map the Milky Way's history, not by light from stars, but by dust from their debris. Chemistry is the quiet author of that map. Every molecule we identify in Atlas carries a clue about pressures and temperatures long ago. The heavy lean toward carbon dioxide may speak of a cradle with a different carbon-to-oxygen ratio, different cooling rates, different grain surface chemistry. The first hints of certain organics would widen the story further, suggesting pathways for prebiotic chemistry far from here. And when isotopes can be read cleanly, when we can separate, for instance, one flavour of carbon from another in a moving, fading coma, the tale sharpens from inference to measurement. Those ratios test our models of stellar burning and element making, not abstractly, but with matter in flight beneath our telescopes. Watch how those signatures drift as Atlas warms and cools, how lines flare near perihelion and fall away after, and you have a laboratory for seeing how heat edits interstellar material. What gets broken, what gets freed, and what remains stubbornly locked. The empty-looking space around Atlas is not empty at all. It is alive with fields and flows. The solar wind, thin, swift, threaded with magnetic lines, meets the comet's expanding cloud of neutral molecules and dust. There, physics turns conversational. Atoms are ionized by ultraviolet light. Fragments form and vanish in microseconds. Emission lines bloom that never occur in air we can breathe. This secondary chemistry adds its own handwriting to the spectrum, distinct from the sublimation that feeds the coma at the source. A solar probe in the right place at the right time can feel the comet's breath as a ripple in the wind, a small perturbation carrying the signature of outgassing rates and composition. To read that ripple, we pair instruments with models, magnetohydrodynamic simulations that follow charged particles through expanding gas, through fields that twist like invisible ropes. The math is heavy, but the payoff is elegant. A prediction you can compare, line for line, with what the spacecraft reads. Dust, too, is a world. The odd polarization measured for Atlas hints that its grains are not the familiar soot and frost of our local comets. Perhaps they are bright-skinned or tangled, crystalline or layered, shapes that scatter light in ways terrestrial analogues rarely do. In laboratories, we build stand-ins and blast them with light to see how they shine. We compute how refractive index and structure twist polarization. Then we turn the knobs until the model looks like the sky. Atlas pushes those knobs toward corners we don't visit often. As the comet nears the Sun, polarization may shift, evidence that grains are changing, coatings evaporating, aggregates breaking, new material erupting from deeper layers. That time sequence is a diary of dust. Heat brings risk along with revelation. When a nucleus warms unevenly, when one side bakes while the other chills, stresses accumulate. Pores expand, cracks lengthen. Gas trapped beneath a crust may pry at its roof until it fails. Fragmentation can follow. A sharp jump in brightness, a brief spray of pieces, and then a string of small fading companions in high-resolution images. The porous, layered interiors, typical of comets, make them strong in some ways and fragile in others. Atlas's early stirring may have already traced fault lines that perihelion will test. Spotting a breakup requires both angular resolution and persistence, and perihelion's awkward geometry puts the best eyes in a bind. But even if the moment is missed, the aftermath tells its own truth. Fragment velocities, dust yields, and the way activity persists or dies all point back to what the interior was like before the stress. Comparisons sharpen the picture. Oumuamua came and went with no obvious gas, yet it nudged itself with a force that looked like outgassing without the usual traces. wrapped in a shape and spin that stretched our models. Borisov, by contrast, behaved more like a local comet, water vapor, dust, a tidy correlation with solar heating, though even it wore chemical quirks that set it apart. Atlas is neither twin. It wakes early, glows green, brightens steeply, and shows a sunward feature that resists easy classification. From a sample of 3, you would never dare publish a taxonomy, but you can say this: diversity is the rule, not the exception. Each traveller drops a pin in a different corner of parameter space. With more pins, the map appears. Peering inside a small, dark, distant body takes models with many moving parts. Thermal codes vary conductivity, porosity, and composition. They swap rotation rates and layer thicknesses. They test how heat slides through voids and along grains. Many parameter sets can mimic the light and spectra we see. That ambiguity isn't a failure, just a reminder that nature gives us outputs and asks us to infer the inputs. Early activity points toward either a nucleus rich in low-temperature volatiles or an interior that helps heat travel farther, faster. Layered models, where distinct ices wait at different depths, fit the way chemistry has switched on by steps. 3-dimensional simulations, with real topography and patchy activity, catch asymmetries like the ones Hubble recorded. They're expensive to run, but they return predictions you can test with the next night's data. Velocity, meanwhile, is a silent hint about origin. Atlas moves fast relative to the Sun, fast enough to make escape a foregone conclusion. That speed carries memory, the push it received leaving home, the nudges from stars it brushed by in the long dark afterward. Rewinding those influences is statistical, not surgical. You don't get a return address, but you do get likelihoods. Thick disk kinematics rather than thin disk, a probable birth among older stars. High speed out of our system means high speed into the next it drifts past, giving some other sky a brief, faint visit. And in that passing, a little material may be exchanged. A grain here, a molecule there, nothing dramatic, just the galaxy at work, mixing itself slowly. Simply observing Atlas would be easier if it were brighter, slower, and better placed against the sky. Instead, we have a moving target in bad lighting, and so technique becomes everything. Telescopes must track along a predicted arc that is never perfectly known. Slit spectrographs must be held steady on a point of light that wants to slip. Adaptive optics fight the air. Weather vetoes the best laid plans. Then there's solar conjunction, which drags a bright curtain across the stage just as the performance reaches its peak. In those moments, space-based assets are not a luxury, they are the show. Spectroscopy has to be clever too. High-resolution observations tease apart crowded emission lines to measure velocities and abundances with care, but they demand light, more than a small dim comet is happy to give. Multi-wavelength campaigns stitch together ultraviolet, visible, and infrared, each with its favoured transitions and diagnostic tricks. Doppler shifts in the line profiles reveal how fast gas streams outward and in which directions, sifting gentle global expansion from narrow directed jets. Time-resolved spectra watch ratios and intensities evolve from night to night, catching chemistry in the act of changing. Polarization spectroscopy adds another dimension, bringing geometry and molecular physics into the conversation. All of it together builds a portrait that no single technique could achieve alone. Through perihelion and beyond, chemistry will keep turning pages. Early on, CO2 wrote the bold headlines. As temperatures climb, more species elbow into view, some as parents, some as fragments produced by sunlight. Cyanide's steep rise is a case in point, a switch-like response that suggests thresholds crossed and pathways opened. Organics may show themselves as larger molecules break down into recognizable pieces. The sequence in which lines appear and fade encodes the comet's interior stratigraphy, what was where, and how deep before sunlight arrived. When the comet turns away and the heat backs off, another lesson begins. Which changes stick, which reset, and which leave scars you can read in the light. Finally, there is the puzzle of that sunward glow. In the familiar story, radiation pressure pushes dust away from the sun, carving tails that point outward. Atlas seems to sketch a line the other way. To explain it, we may need to widen the script. Charged grains can ride magnetic fields along paths that have little to do with photon pressure. Gas could shepherd dust forward if jets are directed, and strong, dragging small particles into a fan that projects sunward from our perspective. The interplay of size, charge, and field orientation matters, as does the way the nucleus breathes, where vents are, how they pulse, whether they align with the subsolar point. Projection effects can masquerade as reversals too, stacking dust into bright planes that look like spears. Somewhere in that web of forces and viewpoints lies the mechanism Atlas is using. Gas drag, electromagnetic guidance, and geometry are all candidates. What we can say for now is simple. The particles are telling us a story about motion, charge, and flow that doesn't fit a single tidy model. Reading it will take more measurements and patient thought, because the patterns we see may emerge only when several forces balance in just the right way, creating transport that differs from simple radiation pressure acceleration. To make sense of that perplexing sunward glow, teams are building digital comets inside their computers. Worlds with real magnetized winds sweeping past them and outgassing that turns on and off in patches rather than everywhere at once. They drop 3i Atlas into realistic electromagnetic environments, let gas burst from discrete vents, mix dust of different sizes and charges, and then track how those particles fly. When the simulation is honest about the chaos, about tangled fields and uneven breathing, it begins to draw the same odd shapes we see in the sky. The aim is simple: reproduce the strange morphology first, then work backwards to the processes that sculpted it, and finally understand why a feature that ought to point away from the sun sometimes seems to lean toward it. Heat, inevitable and patient, writes a parallel story beneath the surface. As sunlight sinks into Atlas, it paints the nucleus with gradients. Warm here, cooler there, so that sublimation starts at different depths, not just on the skin. Capturing that behavior means modeling heat flow through a body that is not a smooth stone, but a sponge. Porous, heterogeneous, threaded with voids, perhaps layered by history. Diffusion calculations test how swiftly warmth moves, given a particular conductivity, porosity, and blend of ices. For materials like those in many solar system comets, substantial heating is usually required before interior layers cross the threshold to evaporate, and yet Atlas stirred early. That means either the interior conducts heat with unusual efficiency, or its recipe is dominated by species, carbon dioxide and carbon monoxide among them, that slip into gas at temperatures far below water's. There is feedback everywhere you look. When ices sublimate, they rob their surroundings of latent heat, cooling the very layers that produce them. Gas that finds a pathway to the surface can enlarge that path, which in turn alters how heat travels the next hour, the next day. These coupled processes are non-linear and messy. A crack opens, a vent blooms, a plume cools its source, the plume wanes, heat shifts sideways, another pocket wakes. Theorists fold that dance into their codes, then compare the output with thermal emission measured in the infrared. Faint glows that trace subsurface temperatures if you have sensitive instruments, and the patience to subtract the sun's reflected light. As Atlas rounds perihelion, those measurements will test the models in real time and may reveal a thermal personality particular to interstellar bodies, born elsewhere, built differently. Dust does not just fall away, it charges. In the solar wind's electric and magnetic fields, grains pick up charge and feel new forces. Their motion becomes a balance among gravity, radiation pressure, gas drag, and electromagnetic nudges. Advanced particle dynamics simulations treat each grain as a traveler with its own mass, size, charge state, and local field lines to follow. In those runs, you can tip the parameters and watch trajectories warp into shapes that look eerily like the sunward extension Hubble saw. It is a reminder that the space around a comet is as electrical as it is gravitational, that a charged speck may choose a path photons alone could not explain. If you're drifting off to this slow unraveling of a distant visitor, let it carry you. And if you'd like more calm, long-form space stories, consider liking and subscribing to Space Historian. It quietly helps these deep dives reach the people who want them. Another key, if we can seize it, is rotation. Knowing how quickly Atlas turns would tell us about its shape, its density distribution, and how sturdy it is when the sun starts tugging. Photometric monitoring tries to find that rhythm, tiny periodic flickers as an irregular body shows different faces, or as patches with different albedos rotate into view. The amplitudes are small, often just a few %, so the measurements have to be precise and sustained. Rotation matters for heating too. It dictates where noon lands and how long it stays, carving patterns into outgassing that can be read in the coma's asymmetries. Spin too fast, and centrifugal stress can exceed the strength of weakly bound layers, prompting mass shedding or outright failure. Spin slowly, and perhaps you're denser than expected, or you hide a surprising internal cohesion. Some small bodies don't spin simply at all. They tumble in non-principal axis states that turn their light curves into puzzles. Those states can be scars of past fragmentation or the cumulative shove of asymmetric outgassing. A firm rotation period for Atlas would be the first of its kind for an interstellar object, a new line on the ledger for comparing alien wanderers with the comets born near home. Visitors don't leave us untouched, and we don't leave them untouched either. Along its track through our system, Atlas will be peppered by solar wind ions that can implant themselves into surface grains, layering the faint isotopic accent of our Sun atop its native chemistry. Interplanetary dust will strike and stick, embedding tiny souvenirs of our neighborhood that could, later on, masquerade as intrinsic signals. The traffic flows both ways. Atlas sheds its own dust and gas into the heliosphere, a wisp of other star chemistry that may be gathered by spacecraft or fall, atom by atom, into our dust lanes. Even Earth leaks at the edges. A trace of atmospheric material escapes to space and might, in principle, meet a passing surface. The absolute amounts are minuscule, but the possibilities matter. When we eventually pass subtle isotopic ratios, we will need to know which fingerprints were there at birth and which were picked up on the road. If we want more than glimpses, we'll need to meet the next Atlas halfway. That calls for new mission architectures tuned to the realities of interstellar targets. They arrive fast, they leave faster, and warning is short. Pre-positioned spacecraft on standby shorten the sprint. Conventional chemical propulsion can do some jobs, but many intercepts require more delta-V than tanks can sensibly carry. Solar sails offer a propellant-free push and mid-mission retuning, though they demand large, delicate membranes and fine attitude control. Farther on the horizon are nuclear thermal or nuclear electric systems, with the specific impulse to chase, pace, and perhaps even return with a sample jar that would change everything. Whatever the engine, the playbook needs pre-approved concepts, streamline decisions, and teams rehearse to move when a new alert appears. The scientific return, composition measured at the source, interiors inferred from flyby fields and images, grains from another star in a terrestrial lab, would dwarf what remote sensing alone can deliver. Between now and then, every detection feeds a growing archive. To turn a list of oddities into a population, we need standards. How to store spectra and images, how to report calibration and geometry, how to merge observations from different instruments and nights into one coherent history. International coordination makes those standards stick. With time, correlations will emerge, links between chemistry and kinematics, between trail brightness and orbital plane, between polarization signatures and activity level. Well-trained machine learning tools may unearth patterns we didn't think to seek and suggest classes we haven't named. But archives must be cared for. They need curation, quality control, and formats that survive the drift of software and storage so that a student 10 years hence can ask a brand new question of a dataset gathered tonight. Theory is moving too. Atlas has forced models to grow teeth, chemistry that evolves in time, porous media that conduct and cool in fits and starts, multi-phase flows that turn a nucleus into jets and veils, grains that charge and discharge as fields change. Numerically, these are hard problems. The codes must juggle fluids and fields, molecular kinetics and sunlight, three-dimensional shapes and real topography. Out of that complexity, new frameworks are emerging for particle acceleration and transport in cometary plasma, for heat moving through heterogeneous sponges, for the way dust and gas braid under competing forces. Each constraint extracted from observations sends the models back to their benches. Each refined model tells observers where to look next. Meanwhile, detection itself is evolving from craft to factory. Present surveys are limited by the size of their mirrors, the quietness of their detectors, and the speed of their pipelines. The next generation improves all three. The Vera Rubin Observatory will sweep the entire visible sky every few nights with sensitivity and cadence that translate into early warning and many more targets. Real-time processing, much of it powered by machine learning, will flag movers as they are seen and estimate orbits quickly enough to cue follow-up while the visitor is still bright enough to study. Space-based surveys under development will erase weather and daylight from the equation, watching continuously and at wavelengths ground sites cannot. With those eyes open, we'll move from a handful of interstellar objects per decade to dozens a year, and from individual case studies to statistics that carry weight. None of this happens in one country or one dome. The ATLAS campaign has been a relay race across longitudes. Telescopes in the Americas, Africa, Europe, and Australasia handing the target off as Earth turns. That choreography takes planning and trust. It also takes shared resources, instruments not everyone can build, expertise not everyone has, time on platforms, terrestrial and orbital, that must be allocated wisely. Standard protocols for sharing files and methods make collaboration routine rather than heroic. The success of this coordination is its own result, a blueprint for the next guest from the dark. The educational wake is broad. Because Atlas comes from elsewhere, it turns the abstract into the tangible. Galactic structure, stellar evolution, chemical enrichment over time become a glowing point with a tail you can photograph. Real-time observing campaigns let classrooms watch science happen as it actually does, messy, iterative, collaborative, and the interdisciplinary nature of the work, physics braided with chemistry, geology with computer science, shows students that modern astronomy is a team sport where many kinds of minds matter. Materials built for this moment will serve the next interstellar visitor, building a public that understands both the beauty and the rigor of what's being done. However it ends, Atlas feels like a prologue. Better detection will tell us if it is typical or a glorious exception. Dedicated missions will turn remote hints into direct measurements and surprises we cannot now imagine. A growing database will let statistics speak clearly about formation paths and evolutionary routes. Trends in detection rates and properties over decades will expose how our corner of the galaxy breathes, how material flows between stars, how often small bodies are made and unmade, how the chemistry of space drifts with time. And the hard-won techniques we're building for Atlas will circle back to benefit studies of our own comets and asteroids, the keepers of our solar system's memory. Zoom all the way in and the story becomes quantum. Photons from the sun are not vague warmth. They are packets with just the right energies to snap bonds and set fragments free. Photodissociation in the coma is a ballet of absorptions and breakups, with lifetimes so short that some species exist only as waypoints on the road from parent to daughter. The emission lines we use as beacons come from electrons dropping between discrete energy levels. Vibrational and rotational states add their own structure, encoding temperatures and densities we cannot touch. In the deep cold of a nucleus, quantum tunneling can open reaction pathways classical chemistry would forbid, perhaps helping to explain unexpected products in Atlas's breath. Even the act of heating is quantum at its roots. Which wavelengths are absorbed, how effectively, by which molecules and grains, determines how energy becomes motion and then gas. A chain we model with quantum calculations and deploy in macroscopic thermodynamics. Step back to the coma and its flows, and fluid dynamics takes the stage. Gas does not seep out evenly. It surges from sources, vents, cracks, sunlit plains, into an ambient atmosphere of its own making. Collimated jets meet that atmosphere and throw shocks. Turbulent eddies mix, cool, and carry momentum. Dust grains are caught up or left behind depending on their sizes and the local gradients. Non-equilibrium is the rule. Different molecules travel with different effective temperatures, and their distributions evolve as the gas expands and thins. Computational fluid dynamics, fed with realistic nucleus shapes and patchy sources, now includes multi-species chemistry to predict not just brightness, but line ratios, not just tail length, but texture. Even so, Atlas's morphology, especially that insistent sunward glow, leans on the edge of those models, pushing theorists to consider boundary conditions and physics we have not yet fully embraced. Threaded through all of this is the magnetism of the heliosphere. The interplanetary magnetic field, carried outward by the solar wind, provides preferred pathways for charged particles, sculpting asymmetries and directing flows. Neutral molecules born from the nucleus drift out until sunlight or collisions ionize them, and once charged they play by different rules. They feel the fields, and the fields can twist them into structures that a neutral gas alone would never create. It is here that plasma and chemistry meet, where a spectral line is at once a chemical signature and a tracer of electric architecture. Photoionization of neutral species in the coma creates charged particles that respond to electromagnetic forces differently than their neutral counterparts. Charged atoms and molecules don't drift from 3I Atlas like soot in a breeze. They weave through space along paths set by a tug-of-war between gravity, electric fields, and magnetism. In the solar wind's restless weather, lines of magnetic force can snap and rejoin. Magnetic reconnection that briefly builds tiny particle accelerators. If such pockets form near the comet, they can kick charged particles to higher energies, imprinting unusual signals or even whispering as faint radio emissions that radio telescopes might catch. Where the solar wind brushes the comet's newborn ionosphere, plasma instabilities can flare, growing into waves that ride the field lines. Detect those waves, and you read the local plasma, its density, temperature, and the shape of the magnetic field threading that region. To predict what we might hear and see, researchers run magnetohydrodynamic experiments in silico, letting the expanding ionizing coma clash with the sun's magnetized flow. Out of those models come testable signatures, ripples at certain radio frequencies, curls of field, and the shifting boundaries where neutral gas becomes a charged, responsive medium. Isotopes offer a different kind of compass, one that points backward in time. With sufficiently sharp spectra, we could one day tease out carbon isotope ratios in Atlas's gases, reading the balance between carbon-12 and carbon-13 as a record of the parent star's mass, age, and metallicity. Oxygen isotopes would trace nucleosynthesis pathways and hint at nearby supernova seasoning in the star's neighborhood when the comet's ices condensed. Nitrogen's isotopic mix would test how efficiently different stellar populations forged that element, locking ancient conditions into a number we can measure. Even the deuterium to hydrogen ratio would touch the primordial story and the processing that followed in clouds and around stars. These are hard measurements: faint target, short exposures, lines packed shoulder to shoulder. They will likely wait for steadier, colder, more sensitive space-based spectrographs. But when they arrive, they will let us test galactic chemical evolution with a precision we've never had. And if a ratio appears that no known stellar furnace can produce, we will need new stories for how and where such matter formed. The chemistry that blooms around Atlas is not a simple chain. It is a web. Hundreds of gas phase reactions compete and feed each other in conditions far from equilibrium. Solar ultraviolet light knocks molecules apart, photodissociation, kicks electrons free, photoionization, and pushes excited states to emit the lines we chart. Where photoionization builds a population of free electrons, electron impact chemistry takes over, driving reactions that never ignite in pure sunlight, and the dust is not just cargo. Grain surfaces provide scaffolds where atoms can stick, meet, and rearrange. Heterogeneous chemistry that can assemble complex organics and leave spectral fingerprints different from gas phase pathways alone. Chemical network models track this living system in time and space, predicting which species peak where, which fade fastest, and which to hunt next as the comet warms. What then could shape a comet like this? Several formation tales fit parts of the evidence. If Atlas condensed in the realm of the galaxy's thick disk, around a metal-poor star, its ice inventory would reflect a different elemental pantry, compositions that could naturally tilt toward the CO2 heavy mix we see. Perhaps it gathered material while passing through a dense molecular cloud, sampling chemistry forged in interstellar space rather than under a single star's rules. It might be a shard from a larger parent, chemistry and structure inherited from a catastrophic collision. Later, thermal reworking in its home system could have cooked the outer layers, distilling and layering volatiles into the stratigraphy now waking. And the very act of ejection, tidal pulls and violent encounters could have riddled the interior with fractures, improving heat transport and gas flow in ways that make its present behavior look unlike our local comets. Each scenario forecasts different observables: isotopic flavors, layering revealed by the order in which molecules switch on, dust properties, activity geometry. Continued watching and better models will let us keep or discard these stories until one remains. In that sense, Atlas is more than a comet. It is a fossil. If its path and speed really do point to the thick disk, we are holding a relic from an older galactic epoch when stars were poorer in heavy elements and the Milky Way structure was not yet what we see today. Some of that record may have been rewritten by cosmic rays and the occasional warm passage near bright stars, but much can remain intact, protected in the cold. Compare Atlas with future interstellar objects hailing from other galactic precincts, and we can begin to draw a chemical map of the Milky Way through time. Galactic archaeology with ice and dust instead of stone. None of this says life. Atlas shows no sign of biology, and interstellar space is a punishing road for anything living. But the chemistry matters. If we find robust organics, it confirms what many suspect, that star systems across the galaxy commonly brew the ingredients life prefers. The inventories won't all match Earth's. Some will be stranger, richer in certain chains, poorer in others. That diversity hints at biochemistries that could, in principle, begin along different routes. Meanwhile, Atlas is a courier in a slow, natural exchange. It picks up a trace of our neighborhood, ions from the solar wind, a dust grain or two, then leaves behind some of its own. Perhaps a future sample return mission will catch a few of those grains, delivering a pinch of other star material to terrestrial labs. Equally, one day an object from another system might carry the faintest isotopic accent of our sun into someone else's sky. The watching we've done already leaves a legacy. Data that would once have vanished into nightly logs now enters shared archives designed to last. Calibrated, annotated, usable by researchers yet to be trained, with tools not yet written. Methods forged to follow this fast, faint, complicated target will flow outward. Pipelines to pull signals from noise, strategies to coordinate many telescopes across many time zones, habits of rapid sharing and careful cross-checking. Citizen astronomers proved their value again, filling gaps and catching transients between the beats of larger facilities. And yes, social media magnified both the truth and the noise, reminding us we must speak clearly about what we know, what we don't, and how quickly that balance can change. Atlas also nudges technology. New image processing techniques, taught to listen for whispers, will help in fields well beyond comets. Machine learning tools for spotting and classifying movers on the sky now run faster and make fewer mistakes. Spectroscopy tuned for rapid cadence on weak sources will serve variable stars, exoplanet atmospheres, and more. Models forced to handle Atlas's complexity, multi-phase flows, porous heat transport, charged dust, will strengthen our grasp of small body physics across the board. And the way we coordinate ground and space assets, pointing windows aligned, data formats harmonized, alerts that move in minutes, will be the default for the next surprise. From here, the path widens. Next generation surveys will lift our rate from a trickle to dozens of interstellar objects a year, letting us ask population questions instead of only case studies. Dedicated interceptors waiting on station will turn "we saw" into "we sampled." A deepening database will expose patterns across chemistry, kinematics, and origin, while improved analysis will extract subtler signatures, faint isotopic tilts, fragile organics, time-dependent quirks that reveal interior plumbing. The field will grow from rare curiosities to a true galactic survey of small bodies, mapping the diversity of planetary outcomes across many suns. In that sense, Atlas is part of a scientific revolution, our first direct access to the materials of other systems, akin to the moment we realize planets orbit other stars. Models that once relied on analogy will have to face measurements head-on. The echoes will reach planetary science, astrobiology, even cosmology, because every grain and molecule carries a record of processes we've only inferred. With each visitor, the universe feels both bigger and more knowable. The wider view is humbling. We live inside a galaxy with open doors. Material passes through, bearing news from long ago and far away, and for a brief while we can read it. interstellar objects like Atlas are messages in motion, crossing stellar neighborhoods and leaving tiny traces behind. Our instruments are finally delicate enough to catch them mid-sentence. That alone should change how we feel about our address in the cosmos. Questions, of course, exceed answers. Which mechanisms truly drive the sunward glow? How common is the steep chemistry we're seeing? Where on the spectrum from typical to singular will Atlas land once we have statistics? How do we read galactic structure from a moving, biased sample of visitors? And the most daring question, among the many natural travelers, would we recognize an artificial one if it came? For now, take a breath. If this quiet exploration helps you drift, you're in good company. And if you'd like more, a gentle nudge to like and subscribe to Space Historian helps keep these night-long journeys coming. Back at the comet, the plasma story continues. Ions shed from the coma don't march straight outward. They thread spirals and kinks shaped by gravity, by electric fields born of charge separation, and by the magnetic field embedded in the solar wind. Where that magnetic fabric tears and reconnects, local accelerators may spark, seeding particle populations whose signatures ripple through radio bands. At the boundary where solar wind and ionosphere meet, instabilities can grow and sing in electromagnetic waves, testifying to the conditions there and the geometry of the field. To anticipate these songs, advanced magnetohydrodynamic models follow an expanding ionizing coma into the flowing, magnetized wind, predicting what instruments should hear and where. Meanwhile, the isotopes wait their turn. With sharper instruments, we will one day read carbon's split between C12 and C13 as a clue to the parent star. Oxygen's isotopic flavor as a map of its nucleosynthetic past and any supernova ash. Nitrogen's mix as a test of how different stellar engines forged it, and deuterium's ratio to hydrogen as a thread back to the primordial. The targets are faint, the lines are tight, and the integrations must be long and steady. It will take the next wave of space observatories to bring these measurements into ordinary reach. Inside the coma's laboratory, chemistry runs on many tracks at once. Photochemical models tally each absorption and break, track electronic excitations, and propagate fragments through a changing field of light, temperature, and density. Where electrons abound, collisions add new channels that pure sunlight would never open. On dust surfaces, atoms and molecules pause long enough to meet and build heterogeneous reactions that may stitch together complex organics. Network models knit these processes into predictions for hundreds of species, telling observers which lines to chase as Atlas warms and cools. And the origin story keeps branching. A birth in the metal-poor thick disk could explain the unusual mixture of ices. A pass through a dense cloud could stamp interstellar chemistry onto the grains. Violent collisions might account for structure and layering that shape present-day outgassing. Late-stage heating near the parent star could have distilled volatiles into separate shelves, and the mechanics of ejection might have fractured the interior, priming it for efficient heat flow. Each path leaves traces we can test as the data deepen. In the end, Atlas is a shard of deep time. It carries the chemistry of epochs when the Milky Way was younger and simpler, altered by radiation and chance encounters, but still legible if we learn the script. Compare it with others from different regions and ages, and we'll begin to piece together a history written not in starlight, but in ice. None of that means life rides along. But if we find robust organic chemistry, we add another data point to a simple claim. The galaxy makes the ingredients. The rest, assembly, selection, persistence, belongs to worlds and their weather. As a project, Atlas has already changed how we work. Archives will keep these nights alive for researchers yet to come. Methods invented in haste will mature into standard practice. The partnership between professionals and patient amateurs will remain essential. Communication will keep mattering, clear, careful, honest about error bars. And curiosity will keep winning, because stories like this insist we listen. Threaded through the plasma once more, a final note. When sunlight strips electrons from neutral atoms and molecules in the coma, those newborn ions stop behaving like their former selves. Photoionization turns them into participants in the electromagnetic game, charged particles that respond to fields in ways neutral gas never can, and that is where the sky around a comet begins to act like a living circuit rather than a drifting cloud.